All right, so now at this point, let's push our understanding a little further so that we're getting closer to formalizing a definition of what it means by having a logarithm function. Okay, so now, to set a solid foundation for this formal definition, allow me to bring out another detail here, a very important detail to understand, that anytime we're learning about a logarithm function, or anytime we're about to learn about a logarithm function, we got to learn about this. Okay, so as I said earlier in the beginning of this lecture, it is strictly required that this lesson here must be learned after I introduced about logarithm. Okay, but then as a further consequence, anytime we're learning logarithm, anytime we're learning about logarithm, it has to be learned after, must come anytime we're learning about logarithm, we have to learn that after we've learned about an exponential function. Okay, so I thought we're done with exponential function. Okay, so now, yes, as far as learning about what an exponential function is, we're done. But there's still about 5% of that material left that now it's the right time to bring it back a little bit more. Okay, so now allow me to introduce that relationship, that connection between our function that we, at least those functions that we, without a formal definition, within those functions that I call a logarithm function. Okay, let's see how they are related to the exponential functions that we've learned earlier. Okay, so now I'm going to say, how about relationship? Okay, relationship of a function y equals log base a of x, okay, with an exponential function. All right, so this is the detail that we want to head out for. We want to look at the relationship, because there is a close relationship between a function that in the form the y equals log base a of x, and how that's with an exponential function. So there's always that relationship. So let's find out. Okay, so now allow me to bring back a few things. So from our learning previously, and it got to be a learning prior to this point. So from our learning previously about exponential function, let me bring back a very familiar exponential function. So how about f of x being the function 2 to the x? It's an exponential function. Now the base here is a positive base greater than 1. This base. Okay, and so, and then in the meanwhile, at the same time, allow me to also bring back one function that we have seen earlier in this lecture over here, the log base 2 of x. The log base 2 of x. All right, so these are the two functions. Now this came from a lecture prior to this lecture already. This came from some learning prior to learning about the logarithm. This we just learned within our just 1 or 2 lectures here, and particularly in this lecture we've learned about how we graph this function, the log base 2 function. Okay, and so now we know the graph of this 2 to the x function, and we have also seen within this lecture, the earlier part of this lecture, the graph of this function here. So now allow me to put the graph of the two functions here together in the same graphing space, so that I can later on successfully point out a relationship between the two functions here. All right, so now in that case, let me swing over to my Desmos, the graphing utility that I'm using, so that I can show the graphs here. All right, so this is now my empty graphing space with Desmos, the graphing utility that I'm using. So just as I mentioned earlier, this is the graph for 2 to the x. Our function, this is an exponential function, and it's the function here is particularly 2 to the x. And so this is the graph as we have learned already, as we have seen this already throughout our learning previously. Okay, So now this function, before I bring in the graph for the next function, I just want to now dive into another detail that if this was a formal learning about exponential function, I didn't even have to bother to mention this, because it's just extra detail and because this was just extra detail and not too important at the time where we were specifically learning about exponential function. So, but now at this point, it's important to point this out, that this function, in a way how it looks, now allow me to bring in a horizontal line right here. Now using a horizontal line to sweep up and down, okay, using a horizontal line to sweep up and down throughout the graph. Then this, the way how the horizontal line is indicating, it suggests that this function, and generalizing any other exponential function. An exponential function is a one-to-one function, because for each y value, there's only one x value taken to that. Okay, each x, or so for each y value, there's only each, or another way of saying, back in that concept where it was explaining about one-to-one function, then each y value here, each output here is from exactly one input only. Okay, and so now clearly this is a one-to-one function. All right, and so now having our function one-to-one function, I bring in this concept right here where I did not mention this before. As I said, if I mentioned this before, then it was a little too much. Okay, it's not really that it wasn't important, but it wasn't important at the point, at the time where we only learned about exponential function. But now it's important to mention this, because here I bring in one-to-one function in the intention that if this is one-to-one function, if this function is one-to-one function, this specific 2 to the x function, once it's one-to-one, it can have an inverse. It will have an inverse. All right, it will have an inverse. And so now allow me to pause my statement right here. All I point out now is that this detail was never mentioned earlier when we were discussing about the exponential function. But now, as we look a little further, any exponential function, in the way how the graph is indicating, is a one-to-one function. And so in that way, consequently, any exponential function will have an inverse. All right, and so now we have done a lot of learnings. We have had a lot of learnings about how we can see the inverse of a function, and especially how the graph of the inverse function relates to the graph of the original function. So if this is our original a to the x function right here, some original exponential function, then imagine that we have a 45-degree line right here. All right. So now, ladies and gentlemen, this graph in blue right here is indeed the graph of our function y equals log base 2 of x. G of x equals log base 2 of x. All right. So now back on my board. The graph for the function f of x being 2 to the x is the graph in red, as you can see, as you are seeing on the calculators, on the graphing utility right there. G of x is this function log base 2 of x, and just now I announced that it's that graph in blue. All right, and so let's have a closer look at, and especially I already introduced that, hey, I informed you ahead of time before I pulled up the graph in blue that this function will have an inverse. Of course, at that moment I didn't say what the inverse is. All right, and then I put in that 45-degree line, and then just now I bring in that graph in blue. The graph in blue I only announced that it was the graph for log base 2 of x. All right, so now let's look at the picture between the two graphs, the graph in red and the graph in blue, especially in reference to that 45-degree line that I optionally put it there. Let's sit back and think of the relationship between the two functions here. Now I only want you to focus and focus your thinking to just between the two functions here. We don't have to think of any general function yet. But hey, 2 to the x here is that graph in red. log base 2 of x is the graph in blue right there that you're seeing. Okay, and now the 45-degree line is there. Let's think of what relationship is going on between the two functions. One more time, let me bring the entire picture of the graph in full screen view right there. All right, so this graph in red right here is the graph for our function 2 to the x, and this graph in blue is our function log base 2 of x. All right, so now from our past understanding about inverse function, and I was already saying this function in red, this function 2 to the x will have an inverse. And so now with the graph showing it, then it looks like as an important result here, as an important shocking result, log base 2 of x that we're seeing on the screen right now is the inverse of 2 to the x. All right, so that's an observation right out from looking at the graph. Because the way how we have known already, the way we used to know after we've learned about the general concept of an inverse function, the graph of an inverse function is the mirror reflection of the original function through the 45-degree line. Here it is again. Okay. Right now I have already announced that this is the graph for log base 2 of x. But in the relationship, in the geometric relationship between the blue and the red here, it looks like the blue curve is the mirror image of the red curve through the 45-degree line right here. All right. And that is the reason why I can now formally announce that log base 2 of x, this function g of x, log base 2 of x is the inverse. So that's right now, it comes right through observation on the graphs, okay, by putting the two graphs together. So log base 2 of x is the inverse of a 2 to the x function. All right. So let's note it down, or maybe let me make use of the space that we still have a lot here. So now as an observation, just simply as an observation. All right. So g of x, that equals, that's defined as log base 2 of x. This is the inverse. Okay. I just want to make sure my writing will not be interfere with that picture that I have left on the corner of the board right there. So log base 2 of x is the inverse of f of x. That is 2 to the x. All right. So it looks like we came to a conclusion. I said it was an announcement. Okay. But see, observations through the graph sometimes may not be accurate. Some viewers, or some students who learn from this lesson, if you take this as a conclusion simply through an observation here, that may not be too convincing for some of the students viewing this lesson right here. All right, so how about allow me to come up with a couple ways to explain, because now in the way how I see it, it is already quite convincing to me that log base 2 of x is the inverse of f of x. But somebody can still disagree with me that, hey, in the end, the way you explain right now is completely based on observation of the graph. And I myself been teaching my students that observing through the graphs is not always accurate, because people's looking sense is different. Okay, people's visual sense is different. I see it right now. I see the two graphs as perfectly symmetric through the 45-degree line. Somebody else with different eyesight here can see things slightly differently. So that may not, this observation through the eyes may not be too convincing for somebody that we recognize the inverse relationship here. And so if that's the case, let me now point out a different way how I can convince anyone learning from this lesson that this function, particularly the log base 2 of x, is the inverse of 2 to the x. Okay, so now let's put the graph away. Okay, and in this empty board space right here, allow me to do the following. All right, I mentioned earlier, I have explained earlier, through the graph, at least this was a proven method right here through the graph. But our function f of x being 2 to the x, here we verify through the graph that it was 1 to 1. Okay, so this is no doubt about it. No doubt about this piece of information. And so now once we know that it's a one-to-one function, that we know it will have an inverse. We know this specific function will have an inverse. All right. And so in that way right here, in that way, we actually learn this solid method. If we know this function will have an inverse, then we can go ahead and find the inverse. Okay, we can go ahead and find the inverse. So now it's time to bring back some old learning material right here, some past learning material. So we're starting out with, so now, how about let's find the inverse, okay, the inverse function of 2 to the x. Okay, let's find the inverse of f of x equals 2 to the x. That's our goal right there. So, yes, our function is f of x equals 2 to the x. So step 1, if we recall from our past learning, step 1, we're going to simply just replace this f of x symbol on the left-hand side with a y variable. So we have our equation, turns out y equals 2 to the x. So back in that learning where I specifically taught about the inverse function. And so learning about inverse function has to come at some time much earlier than learning about logarithm and exponential function as well. Okay, it's the way how the learning is for any pre-calculus course, because inverse function is a general understanding about any function in general, and then exponential function or log function belong to a specific family of functions. And so no doubt about it has to come, learning about inverse must come long before learning about exponential function or logarithm function. Okay, and at this point you notice I keep using the term logarithm function, but I still have not given out a formal definition of what a logarithm function is. Okay, by the way, let's get back to this work right here that we're on our way to find the inverse of f of x equals 2 to the x. All right, so now I replace, the step 1 is simply just replace the f of x symbol with the y variable. All right, and so now if we recall from that lesson where I talked about finding inverse function, then after that step right here, we're going to use the next step that I introduced. We're going to interchange the x and the y variable right from this equation. Because right now what we have is an equation, simply an equation y equals 2 to the x. And then now we're going to interchange. We're going to interchange the two variables. So how about x must equal 2 to the y. X must equal 2 to the y. We swap the role of x and y, or we interchange the two variables x and y. So y becomes x and x becomes a y in our equation. And that's step 2. The step 3 is the big step right here. The step 3 is the big step. The step 3, now if you recall from that lesson where I formally taught about generally how to find an inverse function, then I had a corner of my screen. If you recall from that lecture, I have a corner of my screen verbalizing out or typing out the worded instruction for the steps. So step 3 here means, for step 3 we are about to solve this equation for the y variable. We solve this equation for y variable. But now, if we strictly follow that instruction for step 3 right there, solve this equation for the y variable. If we strictly, again, back to what I was saying, if we strictly follow that instruction, it's going to become hard, a little bit challenging. It's challenging in the sense that how do we solve for y? How do we solve for y from this equation? Okay, how do we solve for y from this equation? So now, thankfully at this point that we're learning about logarithms specifically, so here we just learned, here we're finding the inverse of 2 to the x, but we are in the middle of a lesson about logarithm function, and at least we have already been through with the introduction to logarithm. Okay, so now allow me to bring back another past learning, quite recent, not too long ago. You see this equation right here in step 2. This equation right here in step 2 that I circle or I put in a box right here with a red box right here. This is an equation in exponential form. All right, so now as I bring up this term right here, then some past memory is going to come back. This is an equation in exponential form. So somewhere in the lecture where I introduced about a logarithm, I mentioned that anytime we have an equation in exponential form, and we have also done some examples about this kind of problem. Anytime we have an equation in exponential form, we can rewrite the equation. We can rewrite the equation in logarithmic form. Okay, and like I said, we have done quite a few examples in that kind. So now allow me to just remind in a separate space right here as scratch work. So think about this current equation. X equals 2 to the y. This is an equation in exponential form. So we have learned that previously, that if we rewriting this exact equation, but logically in logarithmic form, then it's going to appear as following. This is the power, this is the base. So now I'm talking about the power y equals to log base 2 of the number x. All right. This is, ladies and gentlemen, as a reminder, this is the logarithmic form that we have been quite familiar with. This is the logarithmic form, okay, of the same equation. So this same equation right now in step 2 is in exponential form, okay. But now I just now apply the skills we've learned in the introduction to logarithm lecture right there, and we turn that equation into logarithmic form. Okay, so now with this equation in logarithmic form right here, let's have a closer look. Wait a minute, it's clearly in the form of one single y variable. One single y variable equals an expression in terms of x. One single y variable equals an expression in terms of x. That expression says we take the log base 2 of x. So all of a sudden we realize we have just now solved for y to satisfy our step 3. So now step 3 right here, solving for it, we're looking at y equals log base 2 of x. So log base 2 of x originally came out, the logarithm originally came out as an operation to look for power. What power satisfy this base raised to the power equal that number, but in the end, it's all of a sudden we realized it's also a way to solve. And we also had example problems about this kind of work where we were solving exponential equations earlier. All right, at least back in the introduction lecture where I introduced about logarithm. So just now I've solved for y variable as an expression in terms of x. All right, and so now upon successfully arriving at that based completely on our past understanding and our recent understanding, where we've learned about anytime we have an equation in exponential form, we can successfully turn that into same equation but expressing things in logarithmic form. All right, so now in that way right there, we're almost done. All of a sudden we feel like we're almost done. We realize we're almost done actually. So last step here is to rewrite. So now with this, I'm going to now call that, you see, F inverse. It's a symbol. This is the symbol I introduced back in the lecture where I generally introduced about an inverse function. So now that y value right there can be now regarded as F inverse. So now F inverse, the inverse. That's just an indication to say that this function logarithm base 2 of x as a function is indeed the inverse of this function f of x. But then again, g of x itself, I named that g of x on the other board. So g of x initially was assigned to be the name of this function. So now we're so firm. At this point, we're firm. This hopefully confirms our understanding, and not only as an observation anymore. This confirms our understanding that g of x, now I can formally make that conclusion. G of x is the inverse of f of x that was defined as 2 to the x. All right, so this conclusion just now I have arrived at is perfectly consistent with that observation we've had earlier using the graph or based on the graphs. All right, so based on the graphs, we notice that the graph in blue for g of x here is the mirror reflection of the graph in red here through the 45-degree line. We saw that on the graph. We came up with this. But in case anyone is not too convinced, then we came to this formal math work right here. We came to this formal math work. All right, and so that's how I'm seeing it. So now, alternatively, we can think of another way. So I'm still looking at the solid math work to explain that this function, specifically log base 2 of x, is the inverse of 2 to the x, is the inverse of 2 to the x. If any one of us does not remember about this particular method right here, or in case anyone learning from this lesson have not been or do not recall right at the moment here that about these steps right here to find the inverse function, okay, we can alternatively have a different way to convince yourself that log base 2 of x is the inverse of f of x, is the inverse of f of x being 2 to the x. And of course, I'm still talking about without looking at the graph, okay, and an alternative solid math work to understand about this. So now how about allow me to erase this, and I'm going to bring in another alternative way of thinking to convince yourself, to convince learners, to convince students that this specific function, log base 2 of x, is the inverse of 2 to the x. Okay, so now let me erase this board right here to make some space for myself. So here, instead of finding it, we're going to just use other logical understanding. All right, so here we go. This is the definition, this is the general definition of an inverse function that was introduced in our lesson about inverse functions in general. Okay, so now again, let me verbalize it out right here. Let f of x be a function that is one-to-one on its domain. G of x, or think about any g of x, is called the inverse function of f of x if g satisfies g of y equals x exactly when f of x equals y. Okay, so g of y equals x, let me bring that into a corner of my board right here. Okay, let f of x be a function that is one-to-one. Okay, so we know that our function f of x here is one-to-one. I name that other function just right now, just out of nowhere. Think about if we roll back to that earlier point where I just simply out of nowhere introduced and purposely put the two functions together. F of x is 2 to the x. G of x is log base 2 of x. This is a rule. This is another rule. This rule is called f of x. This other rule is called g of x. But now, think about this definition that's still on the screen right now. This function g of x, the function g of x here can be called, will be called the inverse of f if g of y equals x exactly when. So in that definition, I use the term exactly when. Exactly when f of x equals y. Okay, so let's dive in a little further into this way of expressing things, and particularly with our two functions. G is this function and f is that 2 to the x function, and the truth will become clear. Okay, now admittedly this way of explaining it is a little harder to understand, is a little more challenging to understand compared to the other the method, but I'm mentioning this again in case anybody viewing this lecture hasn't been taught about the steps to find inverse function. Okay, the steps to find inverse function, or in case anyone at this moment watching it has faded away with that skills about the steps to find any inverse function, then we can still have this is again an alternative way to convince anyone that this function, specifically log base 2 of x, is the inverse of 2 to the x. Okay, so here's how I'm seeing it. So for now, yes, 2 to the x is a one-to-one function. We don't need this information any longer. So now, how about from that, I'm gonna really call this. Okay, let's call that y equals 2 to the x. So y equals 2 to the x. Because see, we traditionally use the y variable as the output for a function. So for now, y is the output function of this 2 to the x function right there. The output value for this 2 to the x function. Or another way of saying, okay, y equals f of x. That's what I'm saying right there. And so now, g of x on the other hand, was defined as the log base 2 of x. This phrase exactly when, logically speaking, it's equivalent to this symbol right here, the double head arrow. That is the symbolic way of saying exactly when. Formally speaking, here and there you might hear people say the word if and only if. That is exactly the same logic. Exactly when, that's another way of wording it, or symbolically the double-headed arrow. Okay, but now g of y equals x if and only if, or exactly when f of x equals y. You see, think about the function g. So g of x or g of y is, the y is just the variable's name for the input. It's not important, but the name of the function here regards to the rule. So g of y here means we apply this rule, take log base 2 of y. So this rule over here, take log base 2 of y. So g of y says we're going to take log base 2 of y. Okay? On the other hand, y equals 2 to the x. All right? So isn't it obvious that this is exponential form that I brought it up earlier. And I mentioned this in our lecture about the introduction to logarithm. So this is an equation in exponential form. All right. And so now with this, then think about that. With this exponential form. Now I just realized I wrote this down a little too rushed right here. In this exponential form, think about, we have been fluent at this point that once we have an equation in exponential form, we can rewrite it. See, that's why it means, or exactly when, or if and only if, we can rewrite this equation as now in the logarithmic form here. Log base 2 of y. Look exactly at the way it is right now. Log base 2 of y equals x. So from this known form, y equals 2 to the x, our equation appears to be in exponential form. And then it's in exponential form and it's logically equivalent, or it's if and only if, or exactly when. So y equals 2 to the x is exactly when log base 2 of y equals x. Y equals 2 to the x is true exactly when, or equivalent, logically equivalent to log base 2 of y equals 2 to the x. I mean log base 2 of y equals x. But log base 2 of y equals x right here, look at a little further. This means what? This statement right here is the same as saying g of y equals x. G of y equals x. And then in the meanwhile, this y equals 2 to the x is the same as saying this is f of x, 2 to the x is f of x, and y equals f of x. So at this bottom statement right here, isn't it making it clear, isn't it? Just making it clear that once we define our function g here being the log base 2 of x, provided that we have also defined previously a function f of x to be 2 to the x, then g of x, this function g has that relationship with f of x. See, g of y equals x. Exactly when f of x equals y. And it's matching and it's perfectly consistent, agreeing with the definition being stated on the screen, corner of the screen right now. So this is another way of convincing anyone, and convincing me, convincing you that this function g, defined as a logarithm, is okay, so now we've had all of that. I brought up 3 different ways to convince anyone. Okay, so 3 different ways. Now we have enough evidence to say that g of x, in this case defined as a log base 2, is log base 2 of the inputs. That function is the inverse of f of x that was defined as 2 to the x. That's how it happens. All right. And so now at this point, so now let's have a closer observation. Okay. Right here at this statement, at this final conclusion, this is a conclusion. Okay, this is a final conclusion. And we can hopefully go from this conclusion to generalize more generality right there, to generalize a broader, a larger generality. Okay? The function, the exponential function, this is an exponential function. This is a logarithm function. The exponential function is base 2. The logarithm function is in base 2 specifically. And so now look at the relationship between these 2 functions right here. This log base 2 of x is the inverse, exactly the inverse of 2 to the x, base 2 raised to the x power. Log base 2 of x is the inverse of base 2 to the x. So think about it. What about log base? What about if it was g of x defined as log base 10 of x? What can we generalize? So think about it. If this was log base 10 of x, then as a wild guess right here, or as an educated guess actually, can this be log base 10 be the inverse of f of x defined as 10 to the x? See, the same base 10 here. All right, so now I'm going to quickly to verify this. So we have this conclusion for sure, but we want to slowly go from this conclusion to making a generalization for any other logarithm, any other logarithm of other bases. Okay, and that's why now I tackle down at log base 10, another common one that your TI calculator can easily get the graph for you. Desmos can get, any graphing utility can get the graph for you. Let's get there. Okay, so I want to know, is it true or false that log base 10 of x being the inverse of 10 to the x? Let's find out. All right, so now on our graphing space here with Desmos, this is the graph for 10 to the x. Okay, and as far as the graph for an exponential function, the graph of an exponential function, nothing should surprise us. Okay, and here we go, the 45-degree line right here. And another thing to another reminder over here, this function in the way it looks, if we put in a horizontal line test right here, how about for now, let me hide away the 45-degree line right here and just simply sweep a horizontal line right here. Okay, so the horizontal line, anywhere we place a horizontal line, okay, then the horizontal line only intersects the graph at one point right here. So that's one perfect technique to decide that this graph right here for 10 to the x is a one-to-one function. So it will have an inverse. All right, so now again, this is the 45-degree line. And so log base 10 of x is right here in blue right there. And so we have that mirror reflection relationship again. All right, and so now allow me to only, for this particular relationship right here, allow me to only stop right here after explaining through the graph right here. I don't want to go back and explain throughout all the steps of finding the inverse of 10 to the x and then to arrive at log base 10. But now, so we were convinced earlier, we were clear earlier that log base 2 of x is the inverse of 2 to the x. Just now graphically we agree again that log base 10 of x is the inverse of base 10 to the x. So base 10, base 10, base 2, base 2. All right, so now one more try over here. So what about, now I'm going to put in a different pair of functions. What about e to the x? So e to the x, log base e as natural log of x. Is this true? Is this true that, so another question is being concerned here, the question being brought up right here. Is natural log of x the inverse of e to the x? True or false? Or, this statement here saying that the natural log of x is the inverse of e to the x right here. True or false? Okay, one more time, let's swing over to decimals and confirm that result. But another observation right here. Base e to the x. Base e of the log, base e to the x. Base 2 of the log, base 2 of the x right there. Base 2 raised to the x right there. Okay. All right, so again, in my graphing space right here, this is e to the x. Okay, and again, with the horizontal line test, we are clearly convinced that this function, e to the x, is a one-to-one function. All right, and so now this is the 45-degree line, and this is the graph for natural log of x. Natural log of x. All right, and so now once again, the graph for g of x in blue right here is exactly the mirror image of this graph in red through the 45-degree line right there. So in that way, yes, it is true. So now it's not any longer a question mark. It's no longer a question. We are clear again that log base e is the inverse of e to the x. Log base e of x is the inverse of e to the x. All right, so now after a few problem, we check and we check, we try and we confirm, we checked and we confirmed. Okay? So now we are ready to come up with a generalization right here. Okay, so now generally speaking, so we investigated thoroughly with 2 to the x. So it came out log base 2. It came out that log base 2 was the inverse of 2 to the x. We investigated through the graph right there, and it shared that similarity. And so log base 10 of x is the inverse of 10 to the x. And we also just now, log base e of x, or natural log of x, is the inverse of e to the x. And so now we can come to the following generality right here. All right, so now generally, all right, as a further important impact for our understanding. Let me write it in a formal form here. Any function g of x that's defined as log base a of x, a general base, okay, is the inverse. All right, is the inverse. So that's just a conclusion, and that's a conclusion that's blended together with our past learning. So anytime we're looking at a logarithm function, a rule that say takes logarithm base a of an input, that function there for sure is the inverse of some function f of x defined as base a to the x. All right, so this conclusion is important. And of course, let's add in that important understanding right here, where a is a base positive and a has to be other than 1. All right, the base is a positive and other than 1. Okay, so, but this is now just a generalization about all logarithm base a, any function that's in this, under this general definition, a logarithm base a of an input, that function must for sure be, the inverse of an exponential function, the inverse of an exponential function, and namely that exponential function, base a to the x. All right, such an important conclusion, such an important generalization right here that we've arrived at. All right, so now, ladies and gentlemen, here we are at a formal definition. This is not the one yet, okay, but now here we are at the formal definition. And so, sadly, I wrote down this because I want to save the other space of my board for a later example. So how about right here, allow me to delete this line, erase this line right here, even though I wrote it down not too long ago. But now we are ready to take the formal definition of what a logarithm function is. So here we go. It's been a long time since the lecture started until now. This is our first moment that I introduced the formal definition of a logarithm function for any general logarithm function. All right. So before I really write down the wording of this, I have to clarify a little more. So earlier when I have a log base 2 of x, earlier in that lecture I wrote down a few rules that involves log base 10 of x, and then there's a log base the 3.5 of x. We worked through our examples, and then log base 4 of x right here, and then log base e of x right here. Generally speaking, with these, simply just a log operation with a base, log operation with a base of an input. Any one of these, I already used that name, a logarithm function. But now less specifically, so I'm going to use that name again, but that name rings a bell that it's in the form of a particular logarithm of a base right here to an input. And then so now what exactly is that? Okay, what is exactly a logarithm function? So I use a name, but what exactly is that? All right, so the logarithm function, okay, or precisely speaking, the logarithmic function, okay, of the form. Because so for now, all logarithmic functions we have learned is only of the form as following. And this is the only one that we call logarithmic function. The logarithmic function of the form f of x equals a log base a of x. Okay, we take the log base a of the inputs. And this logarithmic function right here I underlined, but just now I realized I should have written that in red ink right here. So how about allow me to change that to red ink right here to really catch your attention. So now formally we call it with the name the logarithmic function, okay, the logarithmic function of that form right here. So I indicate specifically that we're looking at this form right here. You probably gonna start having some concerns in your mind that, or deep somewhere in your mind that, is there other forms of a logarithmic function? We'll get there, okay. But for now, right at this form, just that simple form where it's a logarithm base a of the inputs, just directly into logarithm base a of the inputs, okay. Yes, where a is positive and a is other than 1. All right. Anytime we have the base of a logarithm operation. So see, this is a function in a way how I see it. The function here, as a rule, is stating that we take log operation in respect to base a of our inputs. And then that simple form right here, I call that for now the logarithm function, the logarithmic function. And so the logarithmic function in this form, because I'm not talking about any other form yet, provided the base is positive and the base is other than 1. Okay, so now that logarithmic function is defined as the inverse. Okay, any logarithmic, later on as I extend this definition, I'm going to point it out even further. So this logarithm right here is defined as the inverse, okay, of the function, a specific function right here, f of x, I mean a function that's in a form. How about y equals, because I already used f of x for this, so y equals a to the x. Y equals a to the x. All right. A to the x is an exponential function. And so now generally log base a of x will be, well, we call that logarithmic function. But then exactly a logarithmic function is the inverse of a to the x. That's how we define a logarithmic function. All right. All right, so now at this point, we have already just now realized that realized how important we have just realized that important connection, that important relationship between a logarithmic function, and an exponential function, and how tightly related they are. Okay, so with this understanding now, in the way how I see it, without working with an exponential function, then there would be no reason to define a logarithmic function. Okay, so the world would not have a logarithmic function without having to work with an exponential function. That's how I see it, and that's to point out how important it is that we have to know an exponential function in order to lead to that definition, that formal definition of what a logarithmic function is. Okay, and so now now that we've realized how important it is that a logarithmic function is related to an exponential function, and now allow me to bring in another detail about an exponential function. Yes, a detail about an exponential function. This detail was not brought into my teaching earlier in the earlier lecture where I taught about exponential function. The reason for that was that if I brought this detail into that lecture where I earlier introduced about exponential function, then at that point in your learning, bringing in this detail would not be very practical, would not be very productive. Okay. On another hand, bringing this detail into that lecture earlier when I was teaching about exponential function would make the lecture to become a little too lengthy. Okay, where the information at that point to be taught would not be too productive. And so now, but at this point now, it's just the perfect timing to bring in this, bring in this detail right there, so that we can use this detail as to enhance our understanding, to emphasize our understanding with exponential function, and again use that detail we're about to learn here into deriving another important understanding of regarding the logarithmic functions. All right, because now it's no doubt that logarithmic function is so heavily related, so closely related, or so tightly related to an exponential function. Anywhere we're working with a logarithmic function, anything that we're about to come up for the logarithmic function, it must be somewhere originated from an exponential function. That's the way how I see it. All right, and so now let's dive into that. So now let me start with that detail about an exponential function that was not taught before officially. Okay, and now we're gonna formally bring it out. So now I would like to talk about domain and range. Okay, domain and range. So yes, tentatively I aim at eventually pointing out the domain and range of a logarithmic function. But let's start out learning about the domain and range of an exponential function. Okay, so the domain and range of an exponential function. All right. So that's right now our objective of this particular topic right here. So at this point in your learning, we are currently learning about logarithms, but looking back at an exponential function, then this is what we should have known at this point. So an exponential function is an a to the x in that form right there, and just allow me to tackle right down with the simplest case. The simplest case we've been through with the lessons about the exponential functions, and there were a lot more than just a simple a to the x. So here, let's just tackle down. Let's just build our understanding from the case of a simple exponential function first. Okay. And so with this simple exponential function, simply a base raised to an exponent. The base is again has to be a positive value and other than 1. Okay, but now with just those two requirements to be the base of an exponential function, we already learned the following, and so allow me to explain the detail about domain and range of an exponential function through the graphs right here. Okay, allow me to give a graphical explanation rather than just focus too much on the mathematical work, on the mathematical side of that. All right, so now we've learned previously that when the base is when the base is a value greater than 1, because base has to be other than 1 specifically. Okay, so now when base is greater than 1, we have learned already that particularly for this simple graph right here, for this simple function right here, simple exponential function, then our graph is the following. It's a curve that's rising one way from the left to the right. Okay, and we also learned even a lot more details than just this. We had a y-intercept at 0, 1. Okay, the graph is rising from the left to the right. It has a horizontal asymptote here. And the graph, so now I would like to emphasize this. I also mentioned this, but did not have a chance to emphasize that. The graph for this function stays completely above the x-axis. The graph stays above the x-axis. All right. Allow me to quickly swing over to my the graphing utility with decimals again. All right, so we have seen those activities before, this demonstration that I've done before. So these are on my decimals graphing utility here. Let's quickly again investigate all of those graphs where the base is greater than 1. So I have a lengthy list of those exponential function, and I didn't even have to bother typing it in informal notation right there. But these are the exponential function, the simple exponential functions where the bases here were all greater than 1. So 1.05 to the x has this base right here nearly flat out, but if we put it in a very far zoom, it's a rising one-way graph from the left to the right, and the curve is completely above the x-axis. Okay, just like what I was explaining on the board earlier. And then we moved on to 1.25 to the x. Now I can turn off that the yellow curve away. And so now the green curve is making the story even more trivial. The graph is again in the same shape right here. Rising is a curve rising from the left to the right. And the curve stays completely above. The curve stays completely above the x-axis. And then now I'm going to turn on, I'm going to show 1.5 to the x. Okay, and now I can turn off that green curve right there, and 1.5 to the x. The curve again has that exact fundamental shape pointing to from the left to the right. The curve stays completely above the x-axis. And then any of the three curves I've shown so far, any of the three graphs I've shown so far, all have a horizontal asymptote right on the x-axis. Okay, right at the x-axis being the horizontal asymptote. Okay, and then putting it in a far zoom right here can make the story become more clear like that. All right, and they're all going through that same intercept point right here on the y-axis. All right, and so just that. Now I can quickly turn on the other graph right here for 2 to the x, and then 2.1 to the x, and then now 2.5 to the x, and now 3 to the x, and then 4 to the x, and 5 to the x. All right. And so that's one important information I want to point it out as an observation. Okay, and I mentioned this, but now it's time to really dive into that and even emphasize on that. So right now, see the way how I see it out of observations, the y value is always positive. It's just the curve. I mean, I'm writing the y value is always positive simply because the curve stayed completely above the x-axis. Okay, but now, as far as horizontal spreading, this is one more detail that I did not really bother to bring it out when it was in that formal lecture about the exponential function. In the way how and currently we're working with this with the simple exponential function, and it will be the same with any other general exponential function that we've learned. But for an exponential function, look at the way how the graph is. It looks like if we're looking at the horizontal spread of the graph here, then the graph can keep spreading further and further out to the right hand side and keep spreading further and further back to the left hand side without any limitation. Now for the y value, I just now point out through observation, there's a limitation. The y value always stays above 0, stays positive, because the graphically the graph here appeared above the x-axis. Okay, the graph appeared above the x-axis. So that brought up for us the understanding that the y value, the output of the function, has to always be positive. But for the inputs, represented graphically by the horizontal spread of the graph, for the inputs, it can go 0 for the inputs, it can go positive and any positive value, and it can go negative inputs and any negative input for an exponential function. All right, so now that's the output. The input can be the input x can be any value. All right, and so now I'm just verbalizing it out without putting it into a formal understanding yet. All right, so output has to be strictly positive, but then the input can be x, can be any value. Okay, so that's the observation, but that was restricted to the case where the base was a value greater than 1. But in the world of exponential function, the base is not always greater than 1. What about those graphs, those cases where the base was less than 1? All right, so now allow me to erase this because we want to reinvestigate for the different case right here. Now I'm going to erase this case because we're done with that. Now when we are looking at the case where a is a positive value, of course, but less than 1, let's see what's happening for that case. We already learned from our lesson earlier that when the base is a value less than 1, but of course still positive, the graph would be going this way. And I'm still looking at the graph of a simple exponential function. The curve now in this case going one way but falling from the left to the right, going one way but falling from the left to the right. Okay, so that's the shape. But it still has that exact same the characteristic with the earlier case right here. It has an intercept on the y-axis at 0, 1. Okay, and so another thing I noticed, again, another property, another characteristic that's repeated. The graph here stays completely above the x-axis. Okay, that's implying y value, the output of the function, must always be positive, not even equal 0, because we had the horizontal asymptote here. Okay, I have explained that through the graph. All right, and so once again, before I go further, let's swing over to my graphing utility on decimals to quickly investigate. All right, so now on this list of exponential functions, let's have a look at those exponential functions where the base is less than 1. So let's look at 0.25. The graph is a one-way falling graph from the left to the right. Okay, but the graph stays completely above the x-axis. The x-axis is here. The graph in blue here stays completely above the x-axis. And I don't think I need to keep re-emphasizing about the intercept on the y-axis here. Then now I'm going to turn off this curve. Let's now display the other curve, 0.5 to the x. So this is 0.5 to the x. Again, the graph stays above the x-axis, okay, and it's a one-way graph. It's a graph that goes one way, falling from the left to the right, okay, falling from the left to the right. All right, and it's intercepting with that at that point on the y-axis, 0, 1. All right, and then now I'm going to turn on 0.75 to the x. All right, so 0.75 to the x, again, is in that same shape with any other ones that I brought up earlier. Okay, it's a graph going one way from the left to the right and falling as we're going from the left to the right here. It has an intercept on the y-axis at 0, 1. All right, and then 0.9 to the x. Okay, the values with the value being pretty close to 1 now is making the graph looks quite flat out. But in the end, if I put it out in a far zoom level enough, okay, in the zoom level that's far enough, then once again it's still, the graph still displays that same nature. It's a one-way falling graph. Okay, it's a graph falling one way from the left to the right. It's falling, all right, and the intercept here on the y-axis is at 0, 1. All right, and then again, this graph in purple stays above the x-axis. Any of our graph where the base is less than 1 stays above the x-axis. We found nothing on these graphs. We found no portion of the graph, of any of the graph here, that sinks below the x-axis. All right. And so that is now enough for a generality, and that's why I pinpoint down this particular observation right here. The y values is also positive. The graph stays above the x-axis. So it's also the same with the earlier case I brought up where the base is greater than 1. Okay, and so now what about the inputs? Now again, specifically we're working with the case where the base A is less than 1, positive but less than 1. Okay, so it looks like in a way how the graph is. All right, so and for a basic exponential function, then we can see the graph took any of one of these exponential function can take x inputs equals 0 just fine, and that's how it produced this y-intercept at 0, 1 right here. And then having the portion, having some parts that keep extending further to the right-hand side is indicating that any positive value will be defined for an exponential function. And then as the graph can continue, as the graph keeps spreading to the right-hand side further, to the left-hand side further and further, that indicates that the graph can take any negative value. All right, and so again, that same observation I pinpointed down earlier, now one more time I'm repeating it. X value can be any, or the x inputs, right, can be any value, okay, because x is right now symbolically representing the inputs. So input can be any value, but output has to be positive. All right, inputs can be any value, and output has to be positive. All right, and then we have seen these two, at least these two major characteristics clicked our observations, clicked our attention right here, because we have investigated with two different cases already. Base is less than 1 and base is greater than 1. All right, and in that way, so now we come to an important generalization right here, and this is the detail where I said I did not really bring this into the formal lesson where I taught about exponential function, because at that point where I was teaching about that, if I brought in this information, that would be just a little too much, too lengthy for a lecture, where the material here at that point, the detail here at that point was not so practical or so productive. Okay, and so now it's time, it's a perfect time to bring it out right here. So for this basic exponential function, for any of the basic exponential function here, then we have the following understanding. The domain, okay, the domain for an exponential function is just simply now when we're formally communicating about domain, we use an interval notation. Earlier I was writing in written words that x can be any value, okay, but now x can be any value means it can be positive, it can be negative, also 0. And so in interval notation, anywhere between negative infinity and infinity. That's the domain. Officially now that's the domain for this basic or this simple exponential function. All right, and so the range. So what about the range? So just earlier I came to that generalization, I came to that general conclusion that doesn't matter if the base is greater than 1 or less than 1, the y value, the output of the function must always be positive, must be always positive. The graph stays completely above the x-axis. Okay, so at some point, if you've seen that through the graphical illustration earlier, at some point the graph may seem to overlap with the x-axis. Okay, making anyone viewing the graph believe that the graph does indeed touches the x-axis, but no, with super strong computer technology in these days, we can keep zooming in, and eventually at any point after zooming in far enough or close enough actually, okay, after zooming in close enough, we will start seeing some difference. All right, and so in that way, the range here is indicating output is always positive. Output must always be positive. So that means and output is a different way of calling the range, because the range is the set of all possible outputs in our formal understanding of what the range is. And so now it has to be anywhere between 0 and positive infinity in interval notation. Okay, we won't even include y equals 0. We won't even have an output for an exponential function where y value equals 0. Okay, and so now this is the domain, this is the range. That's for now clears our understanding. Everything we've just put up here completes our understanding indeed, okay, about exponential function. And then I will extend this idea to some further to some other generalized case of an exponential function, because we have learned already that an exponential function has more than just this simple form right here. Okay, there are more exponential functions out there other than these the basic one, these simple ones right here. But now we build things from this simple one. All right, so with this, now we officially conclude the domain and the range of an exponential function, even though it's just the simple case right here. Now I'm going to swing over to the other board where the definition of a logarithmic is still there. So the logarithmic function of the form, so now any function where the rule says take logarithm base a of an input x, of a given input x, is called a logarithmic function. But then precisely speaking, any function where we call that a logarithmic function, any function in this form where we call that logarithmic function, is formally defined as the inverse of the function y equals a to the x with this definition. Okay, then again, I want to really nail that down into your mind. In anyone learning in this lesson, a logarithmic function is meant to be always the inverse of an exponential function. That's why learning about exponential function is so important. It's got to come before learning about logarithmic functions. Otherwise, if I just get straight into here you go, here's the logarithmic function, work with that, it would be pointless to learn about what a logarithmic function. Okay, and so now we clearly understand that a logarithmic function is the inverse of some exponential function. And right now it's just the basic case, the simple case. It's just go straight into taking log base a of an input. Then that log base a of an input must be the inverse of some a base a raised to the x as an exponential function. All right, so now in that way, allow me to bring in another detail that when we learn about inverse function, we talked about this, we mentioned about this, we emphasized about this, and now it's time to bring that information, apply that here to advance our understanding on the logarithm function, on the family of logarithm function. Okay, so now allow me to erase this. And so now think about this part of understanding we've had earlier. Just think about if G is the inverse, okay, of f for whatever function f of x that is. If G is known to be the inverse of f, okay, then this is what we knew right here. And it's not really a theorem, but this is some details. I may word it a little slightly differently from when compared to the time that we were learning about this formally. But now in the end, again, if some function is already proven to be the inverse or defined to be the inverse of some other function, then the following the details must be always true right here. The domain, okay, the domain of G. The domain of G is the range. Domain of G is the range of f of x. The domain of G is the range of f of x. And then I'm going to leave some space right here. The domain, indeed, the range of right. This is the domain. This is the range of g of x. The set of possible outputs of g of x, okay, is the originally domain of f of x. All right. So now once we can verify that some function or a function is the inverse of another function, then clearly in this case I named them, see, g and f right here. If we already recognize, if we have already verified that some function g is the inverse of some other function f, then it must be true that the domain of g, okay, is the range of f, and then the range of g is the domain of f. Okay, if g of, and so now allow me to fill in this information. I left this writing here with a lot of space right here. So just think about it in this case, according to what we have just now learned and applying this understanding into what we have just now learned. Here's how I see it. You see, so we already knew. All right, we knew that g of x equals log base a of x is the inverse. Is the inverse of f of x being an a to the x. This is a little extra note that I'm fitting in right here. Okay, we knew that just now because that was really indeed our definition. We define a logarithmic function to be the inverse of an exponential function, and so of course we knew that g of x being a logarithm base a of x is the inverse of f of x. All right, of f of x being the a to the x right here. So that means as an impact right here. Now I'm going to fill in this extra note, and I should have written this in red ink as a matter of fact too, because otherwise it's all in black ink. It's too blended. So how about allow me to erase this and quickly rewrite that note right here in red ink because it's so important for us. Okay, so think about just as what I said right there. We already knew. All right, so we knew that our g of x, if we define g of x as a logarithm base a of x, okay, is the inverse of f of x. That was defined as an a to the x. So we knew that. That's why I wrote it in red right here. So the part I'm writing in black ink at this point in my philosophy is this is general understanding that we already learned from previous long ago learning. But now the red part right here is what we are trying to apply the general understanding into our specific particular learning material right now. So we knew that g of x, okay, being defined as a log base a of x is the inverse of f of x, the exponential a to the x. So now in that means in this case right here, repeating this particular statement right here, it must be true that the domain of g is the range of f. So that's why so now if we apply that general understanding into our specific case where g is the logarithm base a and of x, and then f is the exponential function base a to the x right there, then I'm saying the domain of g of x, that is defined as log base a of x, is the range of f of x that was defined as a to the x. That's one important red note right there. The domain of log base a of x is the range of f of x that was defined as an a to the x. All right. And so now right from this, allow me to extract some information about this. the range of f of x as a general but simple a to the x, like this, a general but simple exponential function a to the x. Thus, the range of this f of x right here on my board, it's still here, 0 to infinity. 0 to infinity. This is the domain for our simple a to the x. Okay? And now this is the reason why. Now if we're looking at the domain of a logarithmic function, the domain of any logarithmic function is the range of an a to the x. That is, in the case here, it's going to be between 0 and positive infinity. Okay, so this is important, but I want to even erase this and write down another final ultimate important statement here. It's already so important, but being so narrow in space, I'm going to leave this out. So now as an impact right here. All right. And let me also just erase this out. So that means the domain of a log base a of x right here. The domain of log base a of x, of some function log base a of x. That domain has to, importantly, being anywhere for inputs only between 0 and positive infinity. 0 and positive infinity. That is, in another way of saying, this or any logarithmic function in this form, a simple log base a of x, can only take positive x inputs only. Okay, that's another way of saying that. Or you can say x is positive only. We only take positive inputs. That's the impact right there. Okay, so now what about the range of g of x? The range of g of x here, generally speaking, being in a role of the inverse of some f of x. And so now the range of g of x has to be the domain of f of x. So that means in our understanding specifically about we're looking at g of x being the logarithm base a of x, the logarithmic function of x, and then we know that it's the inverse of a to the x, the exponential function. Then applying this general understanding into our relationship between g and f right here, then the range of our function g of x, that's defined as log base a of x, okay, is the domain of f of x. That was defined as an a to the x. This is another important understanding. Okay, so the range of a function g of x that's defined as a simple the log base a of x must be strictly the domain of that simple exponential function f of x equals a to the x. And so now again, this is in red ink right here, important understanding, important information. But now sadly I'm going to immediately erase that to come down with the final ultimate statement right here. Domain of an exponential function. The domain of an exponential function. I now officially mentioned that here on this board, and I'm still having that here. The domain of any simple exponential function is all values of x anywhere between negative infinity and positive infinity. Okay, the domain of an exponential function. All right, so that means now when we're looking at the inverse of this function right here, the logarithmic base a, then the range will be this exact domain of our exponential. All right. And so in this case right here, important ultimate statement right here. All right, the range of g of x, or the range of a function that is the simple log base a of x. Okay, so that range right there, it is in the interval anywhere between minus infinity to positive infinity. So outputs for a logarithmic function, for a simple logarithmic function, log base a of x. Log base a of x can give out outputs anywhere between negative infinity and positive infinity. That's what it is. All right, and so now this is inverted statements here. This is inverted statements, and we came to these important understanding. I put stars here. I put whatever that catches your attention. These are the ultimate understanding about the domain and range of a logarithm function. Okay, a logarithmic function. And so now let's just generalize the idea right here. All right, so now on this board, on the other board, I was writing down the information regarding domain and range of an exponential function, a simple case. So now on this board right here, on the other hand, on the opposite way of thinking, here's the domain and range, okay, but of a logarithmic function. All right, logarithmic function. And allow me to just use a shorthand writing right here. Okay, domain and range of a logarithmic function. And so if we define a function f of x to be a log base a of x, okay, or indeed I want to keep two functions together on the two sides of my board. So how about let's call this g of x. So for any function g of x being defined as a simple log base a of x, this is now legally called the logarithmic function. Okay, but then with this function right here, yes, the base is positive and the base is other than 1, but now the domain, as we have learned earlier, we have concluded earlier, now we just really condense all that information into something that quickly catches your attention. The domain is anywhere between 0 and positive infinity. Or another way of saying, the input x is only positive inputs only. And this is now, ladies and gentlemen, the reason why earlier at the very beginning of this lecture I said, you know, anytime we're working with right at that function I brought up, log base 2 of x, when we were working specifically with that function, log base 2 of x, I mentioned that for that function it can only take positive input. But then I used a very loose way to explain that. If you have seen my other lecture about the properties of log, you got some explanation. You will have some explanation. Otherwise, if you have not learned from my other lecture about the properties of logarithm, you can wait until a later part of the video lesson here to get another formal explanation. This is where that part of the explanation is given out right here. Because log base 2 of x that I brought up in the beginning of the lesson here is one among these logarithmic functions. And so for any logarithmic functions, as long as the base here is a positive base and a base other than 1, so log base 2 of x is no exception. So the domain of log base 2 of x, or now generally any log base a of x, has to be only anywhere between 0 and positive infinity. Anywhere between 0 and positive infinity. It won't even be equal to 0. So another way of saying is any log function, any logarithmic function only take positive input. Only take positive input. Only take positive input. All right. And so now that's one striking understanding right there. Okay. And then the range here, right? The range here is anywhere between positive infinity to, anywhere between negative infinity and positive infinity. All right, so that's the range of our logarithm function. And so, graphically speaking, this is perfectly consistent with our understanding in terms of the graphs of these basic logarithmic functions right here. I brought in earlier the graphs for these simple logarithmic functions already. Okay. When a is greater than 1, then the graph goes like this. one way rising from the left to the right and crossing the x-axis at that point, intercepting the x-axis at that point 1, 0. Okay, 1, 0. But see, either way how it is. And I did yell out loud. I did yell out loud when it was earlier, when we were looking at this earlier. The graph stays completely to the right-hand side of the y-axis. That indicates the inputs can only be positive. The x values that, any x value that we're using can only be positive. Okay, and then on the other case, similarly, we have a graph, okay, and then when a is a value less than 1, but of course positive, the graph goes this way, going one way, falling from the left to the right, but again completely stays to the right-hand side, indicating indicating the function, the logarithm-based a function only takes positive x inputs. Okay, and the function is asymptotic at the y-axis right there. All right, and so now if my graph here is making it a little hard to view from my limited space on the board right here, I can quickly swing by Desmos right here and show the graphs again. All right, so on Desmos right here, this is the list of logarithm functions that I've used before in an early activities, in an early demonstration. So let's randomly pick a case where the base of the logarithm is greater than 1. So log base 2 of x, for example. The graph is like this, just consistent, exactly consistent with with what I've drawn on the board earlier. It has an intercept on the x-axis at 1, 0, and it stays completely to the right-hand side of the y-axis. And the shape of the graph is a curve rising from the left to the right. Okay, so being to the right-hand side completely, being completely to the right-hand side of the y-axis here is making it consistent with the fact that our domain of any of these logarithmic function is between 0 and positive infinity. Okay, so just look at another a case where the graph is where the logarithm is with a base less than 1 right here, log base 0.25. The graph in orange right here, okay, points down. It has that same intercept point on the x-axis here, but it still stays completely to the right-hand side of the y-axis right there, indicating that this function only takes a positive x inputs. All right, and then it's the same for any other one. So now if I pull in, no matter how many logarithm functions we're having on this list right here, all of them being put together still produce a very busy image. Once I turn on all of these graphs right here, it creates a very busy image, a very busy picture. But now one thing I see, all of these graphs stay to the right-hand side of the y-axis, even though it's a very busy looking graphing space right now, because we have a lot of logarithm graphs right here, but all of those stay to the right-hand side of the y-axis. That enforces our and confirms our understanding now at this point, our final conclusion. The domain of any log base a of x, any general or any simple log base a of x, has to be anywhere between 0 and positive infinity. No exception. Okay, so logarithm in general takes only positive arguments. Logarithm in general only take positive arguments. Okay, and so that came just straight out from this understanding that I let it in from this. It came straight out from this understanding that the range of an exponential function is anywhere between 0 and positive infinity. So when we understand, once we understand a logarithmic function as an inverse, as the inverse of an exponential function, then the range of an exponential function becomes the domain of a logarithm function. All right, so just like that, when we're looking at the range, see the graph here, any graph that I'm drawing here, not very well scaling, okay, not very well scaled here, but the graph for any logarithm, the graph for any simple logarithmic function, doesn't matter if a base greater than 1 or the base less than 1, the graph will always have a vertical spread, okay, anywhere infinitely positive or infinitely negative. And that's consistent with our conclusion that the range, okay, vertical spread of the graph can keep extending further up and further up, even though, as you're seeing on the picture, in a case where base is greater than 1, the rising part above the x-axis may become slow, but it's still rising actually. It will keep rising, okay? And then the part at the bottom, the part below the x-axis usually stays pretty rapidly. But in the end, as far as the spreading rate here, no matter how far up and down we sweep a horizontal line, we will always reach a part of the graph like that. Okay, and that's how it confirms, as another way of confirming that range of any logarithms or simple logarithmic function is that the entire interval of anywhere between negative infinity to positive infinity. That's an important understanding at this point in our learning regarding logarithmic function. All right. So now that I've made it clear that a logarithmic function, at least a simple one where the rule states, take the log base a of a simple x. Okay? You see, logarithmic base a or log base a of a simple input x. That is a logarithmic function. Okay? If I call that g of x, then this right here, we are so clear now that it is the inverse of some f of x function where it was an exponential a to the x. So clear with that information. Okay, and as a matter of fact, we got to really nail it down. The whole purpose of coming up with logarithm base a of x, okay, is to serve that, is to use that as, or to serve as the inverse. Coming up with a logarithmic function is to serve as the inverse of an exponential function. All right, so that means that we have to keep diving a little more into our understanding we have picked up previously about the exponential function, so that we can see even more. So what else can still be regarded as a logarithmic functions? Because just as far as exponential functions, this was not the only one. As far as exponential function, this a to the x, this simple a to the x is not the only one. Even though it, yes, admittedly, in my instruction, in my style of teaching about exponential function, I always want to build your understanding of the exponential function, all starting out from this simple ones, and then we start building things bigger. And at the end of our lesson there about the exponential functions, we realize there's such a huge family of exponential functions out there. And so, no doubt about that. What about the logarithm function, logarithmic function? The term we use so far, the definition we use so far, focus only on this simple case. We've had that simple case right there. Okay? Log base a of a simple input being defined as the inverse of this simple a to the x. But what about those other cases out there? I mean, are there more than just the simple log base a of x? Because obviously, if we're looking back at the exponential functions, there were a lot more than just a to the x. There were a lot of functions where I define as an exponential function. As a matter of fact, there was an entire family of functions where I define as an exponential function. So what about those cases? Okay, so if we take the inverse of those, will we end up into a logarithm? That's what we want to find out right there. All right. And so I previously, when I taught about exponential functions, okay, then recall that now any function in the form of a coefficient times the base a. You see this coefficient here, this is, like I said, it's just a coefficient, that's a value for c here. It could be positive, it could be negative, but a to the mx plus b, and then after that we add with a constant k over here. I had this definition back at my teaching in exponential functions. So at some point near the later part of our lesson there at exponential functions, about the exponential function, then I made that claim, I made that statement that any function in this form, indeed, a base a, positive other than 1, a base a raised to a linear expression. This is a linear expression, the mx plus b thingy. Okay, a base a raised to an expression, a linear expression, mx plus b, a raised to the mx plus b, and then multiply with a constant coefficient, c, regardless of whatever value that is, positive, negative, okay, and then plus with a constant k over here. It could be positive, it could be negative, it could be 0. Any function in this form is generally an exponential function. Okay, it's generally an exponential function. So I am not going to take your time to brutally make you digest through, you know, the general domain of something like this, because it will involve a lot of math. Every problem, once we change these expressions, it's gonna give a different domain. So I want anyone, as a matter of fact, it's my style of teaching, when it gets to this very general, the most general form of any exponential function, I want my students to build your own experience to find out the domain of anything like this. There's not really a hard rule anymore. Okay, what I wrote down earlier was specifically for this simple one, when it's a to the x, yes, the domain is clear. Anywhere between negative infinity to infinity. Okay, and then the range, that's the domain. DOM of mine is for domain, and the range right here, okay, is anywhere between 0 and positive infinity. This is so clear and easy to see right from the a to the x. But now when it's a to something else, okay, a raised to a linear expression of x and then times the constant coefficient c and plus a k right here, the domain is not so clear to find. Every problem we have to know how to find the domain differently. And as a matter of fact, domain is still easier to find, but the range, okay, so when it comes to this function, domain and range, every problem it has a different domain and range like that. So you can, I want my students, whoever learn with me, to build, to take your own experience you have already learned and find out for your own, the domain and range on each one of these. Okay, but then they will have a definite, any one of these general exponential function will have a definite domain and range right here. Okay, so now, but that's not the important point I'm about to say. But what I'm about to say now is that I want to show how this general form of an exponential function will lead into the existence of a logarithmic function out there. Okay, so just now realize that any function in this form, a lot more than just a simple 2 to the x or a simple pi to the x or e to the x. A lot more than that. It could be something as following. So now allow me to really do an improvise. It just now came out from my thought right there. And also a live example. It was not planned earlier, right when at the moment I thought of this. Okay, so let's think about this function right here. And this is what I meant by a general exponential function. F of x equals, how about 3 times 2 to the minus 2x plus 3. Okay, I'm teaching and at the same time right here coming up with some creative example on my own at the moment right here. Okay, and so minus 2, how's that? So these numbers came out completely random from my mind. Now we have a function to enforce what I meant earlier by, you see, base 2 raised to an expression that's a linear right here. Base 2 raised to a linear expression of x. And then multiply with a constant coefficient 3. And that's why, to guarantee to emphasize the order of operation, I have to put this part in parentheses. And then minus 2. So that's the k. It's a plus k plus negative 2. This is times 3. And this is our base a raised to the mx plus b. All right. So that's a very ugly looking, a very scary looking general exponential function. Okay, there we go, we've had it. So with something like this, see, we can find a domain and the range easily. And as a matter of fact, I made it seem like the domain and range is so hard to find for something like this. It's really not that bad. Okay, it's really not that bad. And as a matter of fact, the domain can always be anywhere between infinity, negative infinity to infinity. That's one hard rule, at least for that domain for any exponential function. Doesn't matter how complicated it is. Like this case right here, the domain can always be anywhere from minus infinity to infinity. But the range, you can always find out. Okay, the range, you know, it takes different steps to find a domain for each different function here. But this is currently not my intention to get into right here. I just want to point out that, you know, anyone learning with me at this point, you should be experienced enough to come up with a domain here. Either you can pull out a graph, okay, or apply your understanding from exponential function that you've learned with me previously to come up with a domain here. And we always stay focused to, you know, well, this function in the end is a transformed version of a parent 2 to the x function. And this function here, we know that the range is always if y equals 2 to the x and y is always positive. Okay, but then this is not the same domain for this one. You can go ahead and think of that as a transformation of the 2 to the x and then start finding out the range right there for that. Okay, but I'm about to end my talk about the domain and range on this function right here, because that's not what I intended to get into. All right. My intention for this particular exponential function that I brought up as an improvised thought here is as following. First of all, let me swing over to my graphing space on the computer screen right there. Okay, with decimals. All right, so on my graphing space right here. All right. Now, ladies and gentlemen, this is the graph for 3 times 2 to the minus 2x plus 3, and then minus 2. This is the graph for it. All right, and so now the reason I did not go too far into talking about the range, because now I know eventually I would bring it up anyway. Okay, and you can use your own math skill to verify. But graphically speaking, this function, this graph, being the graph of our function 3 times 2 to the minus 2x plus 3 minus 2. This graph here has a has a horizontal asymptote at y equals minus 2. Okay, it has a horizontal asymptote at y equals minus 2, and you can observe right from the graph that right from the picture here that the graph will never sink below this line y equals negative 2. Okay, and that now will tell you some truth about the range of this function. But again, I am not going to go any further into that anymore. Okay, and you have your own way of concluding the range of this particular graph, the range of this particular function that I've had on the board. My point that I'm trying to get into, the intention that I'm really getting into, that I have not been able to get to at this point yet, is that this function, if we're now really putting in a horizontal line as a test for 1-to-1. All right, then let's see how it behaves right here. All right, so here we go. That's my horizontal line right there. Okay, so my horizontal line, as I'm sweeping it up and down, as I'm sweeping my horizontal line up and down, okay, then we can see that no matter where I place my line right here, okay, the graph only crossed my horizontal line once. All right, so indicating the importance that I want to point out now is that even though we have such a complicated looking exponential function as this, even though we have such an ugly looking exponential function as that, and I pull the graph, I show the graph, okay, but it's still a 1-to-1 function. This function is still a 1-to-1 function. This is some information that when we when we learned at the exponential function, I didn't want to bring it there. I did not want to bring it there because it would bring nothing good, but making the lecture too lengthy. But now it's the right time to mention any of those. Okay, so we investigated earlier. A simple a to the x is 1-to-1. Clearly, no doubt about that. But now even just a very general case like this, it has a lot involved. The base and raised to an mx plus b, and then there's a coefficient c, and there's a constant k right here. But in the end, the graph, as long as it's still being a as long as it's still being an exponential function, it's still a 1-to-1 function. that you saw on the graph earlier. Okay. Allow me to show the graph right there, and the horizontal line is still there. That's on the screen right there. And that's my point now, is that being one-to-one, recognizing that this function is a one-to-one, we know for sure it will have an inverse. That's my point is. Okay, this function here that you're seeing on the graph will have an inverse. Okay, this function will have an inverse. All right, so let's find it. I'm not going to say what kind of function is this, is the inverse of this. We've learned about logarithmic function. Yes, I understand, but that logarithmic function we've learned there is a very simple case. Just log base a, generally a base a, log base a of a simple x input. But now we're about, and log base a of a simple x inputs, I wrote it down on the board earlier, is simply just the inverse of the simple a to the x function. But now what I'm looking at is a c times a to the mx plus b plus k right there. This is a lot more than just a simple a to the x function. Let's hunt, or let's find the inverse of this function right here, this general exponential function. Very complicated looking, okay? Very ugly looking, very complicated looking, but it's I made it my best to prove that it's an exponential function. All right, so let's get to it. All right, so now on the graph right here. All right, so now with the graph of this function, before I really show them some math work, allow me to demonstrate the following. Here's our famous 45-degree line, and again, this graph in red right here is the graph of our the function f of x equals 3 times 2 to the minus 2x plus 3 minus 2. This is the graph for that general exponential function I brought up on the board earlier. And just before I pulled up this picture in completely full screen view over here, then I pointed out I have proven that it will have an inverse due to the fact that it's clearly one-to-one. Okay, so now this, ladies and gentlemen, as for you to have a preview ahead of time, this is the graph of the inverse function. This is the graph of the inverse function, the graph in blue that I just brought up right here. All right, so now we know it once further, it one more time confirms further that this function in red right here has an inverse. But now we want to look for what function is this? What function that has this blue curve as the graph, at its graph? All right, so now we are mentally ready to learn a new thing right here and push our understanding bigger and larger and further. Okay, so right from here, our goal is to find the inverse of this function. Our goal is to find the inverse of this function. All right, so let's find the inverse, okay, of f of x. Let's find the inverse of f of x. All right, and so we've learned through this. This is the work to find the inverse of f of x after we have already verified that this function will have an inverse. All right, so in that way, now we can just apply the solid steps we've learned way earlier in our lessons about how to find the inverse of a function. So now first step here, I'm going to just simply replace that f of x symbol here with the y letter. Okay, so y equals 3 times 2 to the minus 2x plus 3, okay, and minus 2. So this is really the exponential part right here, and that's just a coefficient, and that's just a minus term right here. Yes, that's how we call it like that. I mean, so first step is to substitute the f of x symbol notation with the y variable. The next step now, I am going to, as it's just a famous number of steps right there, the next step I'm going to swap, or I'm going to interchange x and y, meaning I'm going to switch role. X becomes y and y becomes x. So in this current equation, but after switching roles of the x and y becomes x. So I'm looking at x equals 3 times 2 to the minus 2y plus 3 minus 2. I just now interchange the x and the y variables. They switch roles, that's all. Okay, we swap their roles. All right, and so the next step now is a big step. We're going to solve for y. Okay, in the next step right here, this is solve for y. Okay, so I'm gonna need to use my other board space right there to spend some time solving for y right here. I'll just write it down right here. We want to solve for y. Okay, from this equation, we want to solve for y. And then once I'm done with my other space, and for anyone viewing the lesson here, think of my other space that I'm about to use is to be the scratch word, okay, or some space where you bring in some number of steps into the small area right there. And then I'm going to come back to here just to come up with the final solved expression for y. So the idea now, we want to solve for y as an expression in terms of x. We want y as one single variable equals an expression of x. That's the whole idea of solving for y. And for anyone learning pre-calculus up to this point, you should be clearly knowing our goal of what it means by solving for y. Okay? And so now, our equation from the step 2 right here, from step number 2 was x equals 3 times, so now 2 to the minus 2x plus 3, and then minus 2. So now to solve for y, and indeed, this is y. Okay? And so now back to what I was saying earlier. So now to solve for y, the first thing, I mean, it's just order of operations. Think about if we were evaluating value, if we give a y value for this expression on the right hand side and perform with the calculation, then according to order of operations, exponents must come before multiplication. So it means we have to start out, and in this exponent right here, there's a multiplication and adding and all over. So we have to take care of the exponent part first, and then after that we multiply with 3, and then we minus 2. So this subtraction by 2 right here is the last one, the last of all operations existing in this work right here. If we were evaluating the expression at a given y value. And so now if we solve for y value, we have to go the opposite order of the order of operations. We're going to have to get rid of that minus 2 first. So getting rid, it means I'm just going to add that to the other side. So here's x plus 2 to equals 3 times 2 to the minus 2y plus 3. And that's what I meant by, reversing. So I have to take some action on this minus 2 first, because if we base on the order of operations, this minus 2 comes last. This operation subtracted 2 comes last. And so now as we're solving, then we have to take some action on this last operation first. That's the idea. Okay? And so now x plus 2 equals 3 over that. And so now once again, and when we're at this point, among these remaining operations, this multiplication has to be the last one among these remaining ones. I'm using that term, remaining ones. So in any steps after we have taken care of some operations, then we have some remaining operations left. So this multiplied by 3 is the last one among all of these operations that remains on the right hand side. And so in my next step, I am going to divide both sides by 3 right here. All right, so that gives me the following resulting equation. So the left hand side gives me really a 1/3 x plus a 2/3. All right. And then the right hand side is 2 to the minus 2y plus 3. This is all of the remaining operations on my right hand side. And my left hand side has already become 1/3 x plus 2/3. And all of that equals this exponential form right here. All right, and so now at this point, again, let's bring back some understanding we have had from the lecture where I introduced about logarithms, okay, as just a mathematical operation. Ladies and gentlemen, this equation is what I call an equation in exponential, okay? It's in exponential form. It's an equation, and it has an exponential term right here. Well, admittedly, the other side is not simply a number, some expression, but we've had examples in that lecture where I introduced about logarithm that we can handle an equation like this just fine. Right now, the way I'm seeing it, currently it's an equation in exponential form. That's how I'm calling it. Okay, and again, I just want to remind anyone viewing this lesson, you have already, as you arrive at this lesson here, you must have already been through with my earlier lesson about where I introduced about logarithms, okay, as just a mathematical operation. Okay, so now what can we do with this equation in exponential form? Any equation in exponential form like the one here can be re-expressed, can be rewritten actually. Can be rewritten, so that means we use this double arrow right here. This equation is logically equivalent to saying that, see, this is the base, this is the base, this is the opposite side of the equation, and this is the power. Okay, so now I'm going to rewrite this equation in logarithmic form. So log base, the base is here, so log base 2 of, you see, I emphasize that part on the left hand, on the opposite side of the equation, because that part goes in here. Log base 2 of 1/3 x plus 2/3. Okay, and all that there is equal minus 2y plus 3. All right, so what have I done here? At this point, all of a sudden, I realize I have arrived at, it's the same equation, but I have rewritten it in logarithmic form. All right, logarithmic form. All right, and now from this logarithmic form again, but in the end, it's still an equation. We already gone a long way, and the left-hand side now displays a logarithmic work, a logarithmic operation. The right-hand side still have, the right-hand side here still has some remaining operations left. There's namely minus 2 times y plus 3. There are about 2 operations left, a multiplication and an adding. And we're still on our way to complete solving for y. We have not reached that final ultimate goal yet, but we're still on our way and we're getting closer. Okay, so now again, I've been showing that way to keep track. We still have, on the remaining side here, some operations left. There's a multiplication with the negative 2, and then there's a plus 3. Y multiplied with minus 2, and then plus 3. All right, so now with these remaining, within the 2 remaining operations here, I'm going to have to take care of that 3 first. I'm going to take some action that applies on this plus 3 first, because it's the last one, so I have to take some action on that first. That's the idea. It's the last one among those that still remain. That's what I was trying to say right there. Okay, and so now I'm going to subtract 3 from both sides, leaving it, rearranging it into log base 2 of 1/3 x plus 2/3. Okay, but now I'm going to subtract 3 from the left hand side, and all that there equals minus 2y. All right, so now in every step we keep getting rid of some operation on the right hand side, on the y side, on the side that has the y variable that we're aiming at solving for. Okay, and so now we're so close to a victory right here. On the right hand side we only have one operation left, y multiplied with minus 2, the multiplication. All right, so the action that we need to take here to solve for y here is simply, in the next step, divide both sides by minus 2. All right, and so now allow me to erase the extra notes in red right here so I can have some more space for myself. Okay, and so in my next equation, okay, dividing both sides by 2. So let me write it in red ink right here to catch your attention, but we're going to divide both sides by minus 2, I meant. Okay, divide both sides by a negative 2. It's getting a little hard to see at the bottom, very bottom of my board here. Okay, but then doing that work, okay, taking that action right here on both sides of our equation produces the following. Now I'm looking at a negative 1/2, and then on the left hand side multiply with log base 2 of, and then there's a 1/3 x plus 2/3. Okay, and then it becomes a plus right here, plus a 3/2. That's my left hand side, and all of that there equals y. I apologize for such a small little space left over, but hopefully it's still visible enough to anyone viewing the lesson. Minus 1/2 times log base 2, and then inside of the log base 2 there's a linear expression 1/3 x plus 2/3, close parentheses, and plus after that, plus after the log term, plus a 3/2 constant. All of that there equals y. All right, so ladies and gentlemen, at this point, let's head back. We are ready to head back to the other board right there. So you can call, if anyone have to do this work, I'm not saying that I'm going to make my student to do this work all the times, but if anyone run into a situation with some professors where you have to do this work, this is how you carry it out. Okay, I didn't call it a formal example, okay, because in these days right here, teaching specifically in this material, some professors require their students to be able to do this. Some professors don't have as strict requirements. Okay, so, but in case you have to know, that's how you're doing it. So now with this ultimate final step right here, this is where I say I have solved for y as an expression in terms of x. So now I'm going to head over to the other board, copy and copy down this expression right here, this final solved y variable. Okay. And so now I'm ready for concluding it. So after solving for y here, I'm ending up with y equals, so now it's a negative or a minus 1/2 log base 2 of 1/3 x plus 2/3, and then plus with a 3/2 right here. Okay. Minus 1/2 times log base 2 is a logarithm right here. So we have a logarithm. Okay. But logarithm not only of one simple input x, but it's an expression of the input x. So you give an input x, but it's before we take log, we have to do some expression on that, some mathematical work on that inputs before we take log. And then after we're done taking log, we multiply the log outcome with the negative 1/2, and then we plus the 3/2 right there. A lot of things involved, but in the end, this, ladies and gentlemen, is our solved expression for y as an expression completely in terms of x right here. Okay, such a long work right here. I may have at this point forgotten what goal are we doing already. What goal were we heading out for in the beginning? Ladies and gentlemen, that goal is here. We want to find the inverse of f of x. We follow the steps that was instructed from a much earlier lesson. And then surprisingly, when it came to that step, it took so much work on the other board right there. And then we came to that final answer here, solve for y, that we ended up with this. All right, so there's still one more step. The fourth step right here is to replace this with this f inverse symbol. Okay, so if this is f, then the inverse, now we have found it. F inverse, okay. F inverse of x, okay, is all that. I have so much of a narrow space, so allow me to just simply write f inverse equals y. This is y right here. That's what it is. So now what have we got right here? What have we gotten? This function from the beginning, okay? And I think maybe it's better that I can just, now you can rewind the video at any point to clarify any of the steps I've done. Okay, but now allow me to erase the board here and only leave behind this, only retain this final function that we have solved for y right here. Okay, it's because I want to put the two functions together closer so that we can have a better observation. Okay. So now we found the inverse. And just earlier I called this inverse, the f with the f inverse some function. But really, let's name that the g of x. How about so g of x here being defined as 1/2, negative 1/2 times log base 2 of 1/3 plus a 2/3. Okay, and plus a 3/2. All right. And so now that function f of x was given. So now as a whole story here from the beginning to the end with that function being given. And yes, I call that, you know, general exponential function and etc., etc. But after such a lengthy work, we came to g of x is the inverse of f of x. Yes, g of x is being this ugly looking, and it involved a logarithm. I didn't call that a logarithmic function or anything like that yet, because obviously something like this is a lot more, even though having logarithm involved, but it looks a lot more than just the log base a of x right there that we had in our formal definition. So let's roll back a little bit. I don't want to rushly call this a logarithmic function, and then eventually and then if at some point we found a flaw, we're gonna break down. That's not good. So let's for now only see this as a function that involves log, and it looks a lot more than just a log base 2 of x. Okay, it has a coefficient in front, it has a very fancy stuff in there. But at least one thing I know for sure, this lengthy one is the inverse of that function. All right, so now with this function big one now being the inverse of that, we call this one an exponential function, even though it was a lot more than just a simple 2 to the x. Well, I pointed out at some point earlier as well, we can think of this as a transformed version of a 2 to the x, the simple 2 to the x. So this is a general exponential, but it's an exponential, and it has an inverse. Okay, so now ladies and gentlemen, we can call, see, with our ultimate conclusion as well, that this function here is the inverse of f of x. But f of x in my philosophy is an exponential function. Well, general or specific, in the end is an exponential function. So the inverse of an exponential must be, that implies that g of x is we have to call it that way. Consequently, it's a logarithm. Okay, it's a logarithmic function. All right. Long work, lengthy explanations, but I hope all of those work now, all of those steps now connect, and now it enlightens us some more that, hey, wait a minute. So this is now also a logarithmic function? This lengthy one. Yes, admittedly it involves log, but it's a lot more than just a log base 2 of x. As far as the amount of expressions involved is crazy. Okay, it's a lot more than just a logarithmic function that we used to know. The logarithmic function we used to know and we had in our definition earlier is simply just a log base a of one simple input x. Now it has a lot more than that. But just now I made that further conclusion. This specific one is a logarithmic function. All right, so what just now enlightened us here? I don't want to make a formal proof or anything like that for anyone learning at this point in your learning yet. And once you build enough experience on your own, you should be able to drive your own proof about this. But now we can make a further. So right from this specific example, we just pinpoint that it now can be legally a logarithmic function, simply because this is found as the inverse of that function, where I call that one here the exponential. And so anytime really now nail down this general understanding, logarithmic function comes out to serve the purpose of being the inverse of an exponential. Logarithmic function comes out as to serve the purpose being the inverse of an exponential. And so now no matter how ugly looking your starting exponential is, but once you have found its inverse, its inverse will be a logarithmic function. That's what my point is. Okay, that's what my point is. And so now the generalization, the bigger, the larger conclusion I'm about to make here is that, you see, now let me highlight a few things with red ink right here. So what's in this one right here? It has a log base a, okay? Because base 2 can generally represent any other base as long as the base is positive and other than 1. So this is log base a. But then inside of the logarithm, the arguments of the log here is a lot more than just one simple input. Here, think about this function right here. Once we have given an input, it's not going to directly take the logarithm on the input itself. It's going to take the logarithm on the input after the input times 1/3 plus 2/3 right here. See, I said after. That means once we have given an input, we have to go inputs times 1/3 and then plus 2/3. And then after that, we're going to take the log right there. And so in other words, see the whole expression here, more than just an input, a simple input. The whole expression here being a linear. Okay. This generalizes the fact that where there will be a lot other times, a lot more times we run into the kind of problem where we take a logarithm of a linear expression, mx plus b right here. Okay, that looks just like the one we have. This is m, the 1/3, and this is b, the 2/3. Linear expression. Okay, and then outside of the logarithm, right, we multiply with a coefficient, some coefficient, positive, negative, 1 or 0, a coefficient c, c times a logarithm. Okay, and plus with a constant k. That's what the 3/2 is for. Okay, so k can be positive, k can be negative, but see, now any function in this form right here, this is the generalization I'm about to make right here. Any generalized logarithm of this form right here, involving that much stuff, log base a of a linear expression, multiply with a constant coefficient, and add with a k right here. Okay, any function in that form, any function like that, it's a function being the inverse of an exponential, some exponential. Okay, so now that's all of a sudden I realize I'm a little short at space here. So is a, so log here is short for logarithmic. Okay, so any function like this is a logarithmic function. All right, any function in that form, c times the log base a of a linear expression mx plus b inside, okay, plus k right here. That function there generally now can be considered as a logarithmic function, and that comes to our what I call an extended definition of a general logarithmic function like that. All right, and so now on the graph, now that mystery is unlocked. The blue curve we're looking at, because we were clear that this graph in red right here is the graph for 3 times 2 to the minus 2x plus 3 right here, and then minus 2. Okay, so that's the graph in the red curve. But then earlier I put up this mystery right here. What is the function that has this graph in blue? Now that function is minus 1/2 times a log base 2 of 1/3 x plus 2/3 in parentheses plus 3/2. That's, ladies and gentlemen, the graph for this function. Okay. All right. So now allow me to do the following. So f of x equals 3 times 2 to the minus 2x plus plus 3, okay, minus 2. That is the function that we've seen earlier. Now I'm showing that I'm showing a live scene of how I can use decimals to graph that function. So this is the graph for that. Okay, and so now the logarithm that we have just found, where I claim to be the inverse of this one, where the graph that was in blue that we saw earlier, g of x equals, now it's a minus 1/2 log base 2, and inside of that is the linear expression 1/3 x plus 2/3. Okay, and we can see that the graph keep popping out, being so alike to what we've seen earlier already. And now we are going to add a 3/2. Now the two graphs look exactly mirror image of each other through the 45-degree lines. So let me even put in the 45-degree lines right there. That's the famous line y equals x. And now I can just go ahead and change the color to black and put it in dotted ink. And that's the picture. All right. All right, so now I just want to recap what was just stated over there on my other board right there. But the way how I see it now is that the inverse, in the way how I want my students to now really understand, is that the inverse of any exponential function is a logarithm. Is a logarithmic function. That's one important understanding that I want to really get it, for my students. I want to get it nailed down for my students to take. Whoever learns with me. So just now earlier, just the work there, it took some time to go through the steps. But again, I came up with this function as an exponential function, as a general exponential function, completely improvised. It came out strictly just as as creative thoughts came out. This 3 came out by that moment. Now at this moment, if I'm thinking of that same problem again, I may not come out with that same 3. Okay, but now the point now is that it's in the general form of an exponential function. And so, and then I show right on the screen that this function will have an inverse due to the fact that it's 1-to-1. We verified that graphically. And that's why, and then we spend our time finding the inverse of that, and we arrive at this one right here. And so now that ultimate understanding I wanted to emphasize is that anytime we come to the inverse of an exponential function, this is the inverse of any exponential function. I keep mentioning that it's improvised because any exponential function in this form, as long as we come to the inverse, then the inverse, of any exponential function is a logarithmic function right here. And I made that explanation earlier. And then I eventually lead to that generalizations about, hey, so any logarithmic, because what we observed in here is that a logarithm of whatever base that is, with a linear expression inside and then with a coefficient in front and with a constant term at the end, like that generalization right here. Any log function, any function in that form, any function defined in that form right here is a logarithmic function. And so now, inverted, that's how I stated that earlier. The inverse of any exponential function is a logarithmic function. And so now allow me to rewrite that extended general definition of a logarithm, the logarithmic function right here. So in that way, we come to an extended, an extended definition. All right. So here's here's the formal worded. It's just the exact same version I put in a box on the other board earlier, but now I'm going to write it in informal wording right here as an extended definition of what it means by being a logarithmic function. All right, so any function of the form f of x, being a constant c multiplied with a log base a operation on a linear expression mx plus b. All right, and then after that, plus with a constant k right here. Any function in that form is a logarithmic function. It's a definition, but it's also a confirmation that so combined with what we've learned earlier, a logarithmic function is understood as an inverse to any exponential function. And so that's why in that form, any one of these big expression right here is a logarithmic function right there. And so now from this point on, you can go out there in the world and look at any math journal, any math paper, any math work, any math assignments, and communicate with anyone either learning math or teaching math. And when people ring to your ear the term a logarithmic function, this is a general form right there. And then the cases we worked with earlier, those are the simple logarithmic functions. All right, so that's how it is right now for logarithmic function. So now, right after we have come to that general or that extended definition of a general logarithmic function, let's look at an example where, as a continuation from our earlier examples here, and I'm going to call that example 4. Okay, but let's do the following. I'm going to say we're going to start out having a function. Let f of x be defined as a natural log of x. This, ladies and gentlemen, in our understanding at this moment now, this is a logarithmic function, but the simple version. It's just simply the log base e of x. It's a logarithmic function. Okay? So let's see what we can do with this logarithmic function. So right out from that simple logarithmic function, in this example 4 here, let's evaluate. Now, I'm not going to slow your learning down to just simply put in x equals 1, x equals 2, to put you into, evaluate x, natural log of 2 or natural log of 1. That work is now way over. I mean, we're way over that. Okay? But we do still want to evaluate. So watch out for those kind of problems where we evaluate. Evaluate in math generally means that we take an input, substitute that into a function. But no one ever says the input has to be a number. And that's what I'm about to get in. So let's evaluate f, that's the rule, f of 5 plus h. All right, so that's what evaluate again means in my way of emphasizing it. I want to emphasize that anytime we're doing an evaluation problem in math, especially evaluating a function at a given input, the input doesn't always have to be a number. Here, right here, we have an input being an expression. Okay, an expression. So now what it says here, we want to evaluate the same function f right here at input being the 5 plus h expression. We don't have to know what exactly the 5 plus h expression is for at this moment. This class is called a pre-calculus class. We've learned all the necessary, all the important, the preparation steps prior to the days that you enter a calculus course formally, because all the skills will become extremely beneficial to your learning in calculus. But seeing this, simply taking the whole expression, the 5 plus h, the 5 plus h, okay? And like I've mentioned this joke at some point here and there in our earlier lecture. If classes are face-to-face, I would make a joke to my students that even if I'm putting in f of a dog right here, we're still going to have to take that dog, substitute that into our function, take the dog as the input of our function. I brought up that joke not only just being a joke, but it emphasizes the fact that the way we evaluate function is simply just that. We take whatever given, substitute that into the place of the input. And then we're going to proceed from there on according to the rule. The rule here says take log base e of the input. All right, so enough with the dog here. Take log base e of this input, 5 plus h, because that's what the rule of this function f says. So take log base e of 5 plus h. Okay? And really that's about all we can do. And really that's about all we can do. Okay, it's just a warning of some serious misunderstanding that now at this point we've learned long enough. Logarithm, any logarithm is an operation that applies on whatever arguments for that. This is an argument, but logarithm itself is not something to multiply. So don't do this. Natural log of 5 plus natural log of h, simply because you think this is a multiplication, so distributive law comes in and multiply natural log with 5 and natural log with h, leaving us natural log of 5 plus natural log of h. This is way off the hook. Don't get there, don't go there. It's a serious warning right there. I mean, it's a warning about some serious mistake that can potentially happen to anyone. Okay, so you may feel it's silly at this point, but take that warning of mine seriously. Okay, and so now it's just simply natural log of 5 plus h. We never had any rule allowing us to work any further with logarithm of a sum. So we just stop our work right there. But see, the work at first thought to be complicated, but it turns out simply that's all I wanted you to get comfortable with. Get comfortable with taking an expression, throw it inside a logarithm, and we produce a larger log expression. That's all. Okay? Because just in our definition earlier of a logarithm, then now we can apply, we can apply a logarithm to an expression a lot more than just a simple x, a lot more than just a number. And so now before we get into further and the more complicated type of problems right here, I want you to get used to the idea it's all about we're starting out with one simple logarithm. You can think of that as a logarithm function or a logarithm operation at this point, whatever way you want to think of that. But then the arguments there, now we're going to take an input larger than just a simple x, input larger than just a number. Take that input, throw that into the function. Substitute the input expression into our input variable, and that becomes natural log, in this case, natural log of the 5 plus h. All right. So now, after so much beating around the bush, let's advance on right there. So, and I will come back to this part A some more, but let's do something else before I come back to that. So how about f of a 3x minus 1? So the work here is extremely similar to what we've had in part A. Instead of asking you to substitute x equals 5 or x equals 10 or x equals e into the function. Nope, we're not doing that simple kind of work anymore. We're way over with that. Here I want you to substitute 3x minus 1, the entire expression here as the input, into our function, into our place of the x. Well, there's some confusing x and x here, but see, this is one expression of x. And I want you to take that whole expression of x and substitute that for x in our rule of this function. Okay, so the rule of this function says we take the logarithm, the natural logarithm of the input, but the input is now 3x minus 1. So we consequently produce natural log of 3x minus 1. All right, that's all there is. And so yes, I'm going to put this answer in a box again. It looks surprisingly simple. You don't need to take it any more complicated than it has to be. Okay, let's look at part C right here. This is, how about f of x squared plus 5? Okay. So again, just another practice to strengthen your I mean, or just a practice for me to purposely to make my students overcome with that fear about, oh my God, I have to take something so big into a function. You just gotta overcome that. Okay, no matter how big that is, take that, substitute that for the x, replace that with your x variable in your function. Overcome that fear. Okay, and so now we're looking at the rule of f says natural log of the x squared plus 5. We're done again. Nicely and simple. We're done nicely, and it's a simple answer. All right. But now I have another purpose behind the scene for these problems I brought up on the board right here. So as far as an example, I just want to enforce the fact that anytime it comes to evaluating a logarithm function, a logarithmic function, at this point, see, I can legally use the term logarithmic function now. Anytime we come to evaluating a logarithmic function, then we can throw in really any expression. And the idea now is that one function going inside another function. Okay? But the real purpose I want to point out now is that if you looking at this one, for example, this one right here, So yes, ultimately that came from f of 3x minus 1. But in the end, at the end result right here, this one right here is a logarithmic function right here, because it's a log base e. Okay, the expression inside right here is a linear expression. So I'm trying to point out how this is agreeing with the form being written here as a general form. See, the linear expression inside of a logarithm. And then we don't see a coefficient in that problem right there. It means coefficient 1. And we don't see a constant term here. It means it's at 0, plus 0. And so part of, aside from delivering some problem for you to repeat your skills about evaluating an expression into a logarithm to overcome your fear on that, I also want to introduce that, hey, this is we have ended up with this one here. This one here is a logarithm, okay, function, or a logarithmic function, because see, it has log, and inside of log is simply a linear expression, coefficient 1 and plus 0. And then here, to be even a little more precise, if we are targeting at x being the variable, the input variable, then it's a log function of x. Okay, what about that one? Yes, we have an expression, it's no longer x, but if we are targeting at h right here being the variable, if we're looking at h right here as our variable and 5 is surely just a constant, just a given value right here, then in the end it's a linear expression of h. Okay, so this is, again, it's a log function of this one right here is a logarithmic function of h. See, log, natural log of h plus 5, a linear expression of h. So we also learn right on this example an extra skill that we can confirm for ourselves. I show you how to confirm who among these can be regarded as a logarithm function, a logarithmic function, and who's not. This one, why is it not? This one is, I wouldn't call this a logarithm function. Yes, admittedly, it's a function that involves log, but I wouldn't call this thing a logarithmic function. The expression inside of that is a quadratic, is more than just, it's other than a linear expression. And as a matter of fact, it's an irreducible quadratic here. All right, so something like this, you can call it, it's a function involving log. It's a function with log involved, but I wouldn't call this thing a logarithmic function. All right, so that's all for this example number 4 right now.